Let's solve a parallel circuit. We have 24 volts at 0 degrees running at 15 kilohertz and a resistor and an inductor in parallel. The resistor is 12 kiloohms at 0 degrees. The inductor is 150 millihenries. The first thing we need to do is find the inductive reactance, which is 2 pi FL. And so X sub L will be 2 pi times 15 kilohertz times 150 millihenries. And so X sub L will be 2 times pi times 15 kilo times 150 milli, and we get 14.137 kiloohms. Inductive reactance is always at a positive 90 degrees. Now the resistor and the inductor being in parallel, we need to find the impedance, and there will be two ways to do this. You're familiar with these. We can take the reciprocal of the sum of the reciprocals, or we can use the product over the sum. Now with these vectors, I prefer the product over sum. It seems to be a lot easier. The preference is yours. Remember that if you use the reciprocal of the sum of the reciprocals, you could add in as many components as are in parallel here. If you use product over sum, make sure you know that you can only do this with 2 components at a time. If we had 3, we could combine 2 components first, get a combined resistance, and then combine that combined resistance with the 3rd component using this method, but only 2 at a time. And so I'll do this both ways so that you can see how to do this. I'll use the reciprocal of the sum of the reciprocals first. The impedance will be 1 divided by 1 over R, which is 12 kiloohms at 0 degrees, plus 1 over X sub L, which was 14.137 kiloohms at 90 degrees. Now, when we divide vectors, we know that we divide the magnitudes and we subtract the angles. The numerators of these fractions are not vectors, they're scalars. We'll treat them as though they're at 0 degrees. And that's what we'll always do. Anytime we divide a scalar by a vector, you treat the scalar as though it's at 0 degrees. And so the impedance will be 1 at 0 degrees divided by, and so I'll divide this vector first. We've got, divide the magnitudes, 1 divided by 12 kiloohms, which is 83.333 micro, and that's Siemens. And we subtract the angles. 0 minus 0 is 0, so that remains 0 degrees. Plus, for the inductive reactance, we have 1 divided by 14.137 kilo. The magnitude will be 70.736 micro Siemens. And then we subtract the angles. 0 minus 90 is negative 90 degrees. Okay, and now we can add these two vectors, and to do that we need them to be in rectangular coordinates to be able to add these two. And so if you look at these graphically, we have 83.33 microsiemens, which is at 0 degrees. We have 70.736 microsiemens, which is at negative 90 degrees, and we're looking for the resultant. And so you can see that the two components are at 90 degrees to one another, and we're looking for the hypotenuse of the triangle. And so the magnitude will be the square root of the sum of the squares of the magnitudes. And so we'll have 1 at 0 degrees divided by the square root of 83.333 micro Siemens squared plus 70.736 microsiemens squared. that will be the magnitude of the sum of these vectors. And the angle will be the inverse tangent of always the y component divided by the x. And you can see from the graphical representation that the y component is the one that's at negative 90 degrees. The x component is the one that's at 0 degrees. And so we always want to make sure we take y over x, so 70.736, which is microsiemens, divided by 83.333. And the microsiemens will cancel here, so I'm not going to bother writing those. And so we get the total impedance is equal to 1 at 0 degrees divided by the square root of 83.333 micro, close parentheses, squared, plus, open parentheses, 70.736 micro, close parentheses, squared. And so we get 109.307. 109.307, that's microsiemens. And the angle will be the inverse tangent of 70.736 divided by 83.333. Again, the microsiemens canceled. And you'll notice that we get 40. Oh, I'm sorry, I made a big mistake. The 70.736 microsiemens is negative because it's down. And if I had not skipped any steps at negative 90 degrees, if I had converted this to xy coordinates using the cosine and the sine of the angle times the magnitude, I would have seen that this would have come out to be a negative number. And so let me try that again. The inverse tangent of negative 70.736 divided by 83.333. That's why it's so important to think about the vectors and their graphical representation. 40 degrees is clearly not the right answer. The impedance should be at a negative angle. So I know I had the wrong answer because I can see from the graphical representation. And so the angle is actually negative 40.326 degrees. Now we have one last division to do. The impedance we'll divide the magnitudes. So we're going to have 1 divided by 109.307 micro, negative 6. The impedance is going to be 9.149. That's kilo ohms. And the angle will be 0 minus a negative 40.326. So 0 minus a negative 40.326 will be a positive 40.326 degrees. And so this will be the total impedance of the circuit. So let's see if I can write that here. It's going to be 9.149 kilo ohms at an angle of 40.326 degrees. I'm going to find the total impedance again, this time using the product over sum method, and then the choice will be yours as to which one you prefer. And so the total impedance will be R1 times X sub L. R1 is 12 kilo ohms at 0 degrees, times 14.137 kilo ohms at 90 degrees, and then we will divide by the sum. 12 kilo ohms at 0 degrees plus 14.137 kilo ohms at 90 degrees. And so the product, that's the easy part. The total impedance will be 12 kilo ohms times 14.137 kilo ohms. Right, so I'm multiplying the magnitudes, and we get 169.644. That's going to be mega, and the units will be ohms squared. Then we need to find the sum, and again, if you look at this graphically, we have 12 kilo ohms at 0 degrees, and we have 14.137 kilo ohms at 90 degrees, and we're looking for the vector sum, which would be the hypotenuse of the triangle that's formed. And so we can find the magnitude by applying Pythagorean theorem. The magnitude of this sum will be the square root of 12 kiloohms squared plus 14.137 kiloohms squared. That will give us the magnitude. And the angle will be the inverse tangent of always the y over the x. And in this example, you see that the y component now is positive. So the y component is 14.137. That'll be kiloohms divided by 12 kiloohms. The kiloohms will cancel. So our total impedance will be 169.644 mega ohms squared divided by, and so we'll take the square root of 12 kilo. Let's see. Let me do that again. Square root of open parentheses, square root of open parentheses 12 kilo close parentheses squared plus open parentheses 14.137 kilo close parentheses squared, and the magnitude will be 18.543 kiloohms, and the angle will be the inverse tangent of 14.137 divided by 12, and we get 49.674 degrees. And you can see I forgot to write the angle here. When we multiplied 12 kilo times 14.137 kilo, we had 0 and 90 degrees. We'll add the angles because we were multiplying. The numerator is at 90 degrees, positive 90 degrees. Okay, so don't forget to do that. And so last step is to divide. We have 169.644. That is mega, positive 6. And we're dividing by 18.543 kilo, which is positive 3. And when we divide, we get 9.148. I'm sorry, actually 9.149 kilo. And ohm squared divided by ohms is just ohms. And then we will subtract the angles. We have 90 degrees minus 49.674. And we get 40.326. So we've got the exact same answer that we had when we used the reciprocal of the sum of the reciprocals. And so I prefer this method. I think this is a little bit easier. I don't have to take the reciprocal of vectors and then add them together and then take the reciprocal again. The multiplication part here is a lot easier. We still do have an addition here, but overall I think this way is easier. The choice is yours as to which method you prefer. Since this is a parallel circuit, both components are in parallel. I have nothing in series. I know that the source voltage will be the voltage across each component, right? Now, if I had a component here in series or here, that wouldn't be the case. But because everything's in parallel, I know that the voltage here is 24 volts at 0 degrees. Same thing here, 24 volts at 0 degrees. And so the next step generally is to find the total current. The total current of the circuit will be the source voltage divided by the impedance. Source voltage is 24 volts at 0 degrees. We want to divide by the total impedance, 9.149 kiloohms at an angle of 40.326 degrees. So we're dividing. We will divide the magnitudes, 24 volts divided by 9.149 kiloohms, and we get 2.623 milliamps, and then we subtract the angles, and so 0 minus 40.326 will be a negative 40.326 degrees. So that's the total current of the circuit. We have 2.623 milliamps at an angle of negative 40.326 degrees. Now I can go ahead and find the current on the resistor. Current through the resistor will be the voltage drop across the resistor divided by the resistance. And so we have 24 volts at 0 degrees. The resistance is 12 kiloohms, also at 0 degrees. And so I think I can guess it's going to be 2 milliamps. We have 24 volts divided by 12 kilo, which is 2 milliamps. Subtract the angle, 0 minus 0 is 0. So the current through the resistor is 2 milliamps at 0 degrees. And then finally I'll find the current through the inductor, which will be the voltage drop on the inductor divided by the inductive reactance, its equivalent resistance. And so again we have 24 volts at 0 degrees, and we're going to divide by 14.137 kiloohms at positive 90 degrees. And so we have 24 volts divided by 14.137 kilo, and we get 1.698 milliamps. And then the angles, we subtract them. 0 minus 90 is negative 90 degrees. And so the current through the inductor is 1.698 milliamps at negative 90 degrees. We have the total current leaving the source, 2.623 milliamps at negative 40.326 degrees. That current reaches this node and splits. Some of it flows through the resistor, 2 milliamps at 0 degrees. Some of it flows through the inductor, 1.698 milliamps at negative 90 degrees. And so we'll check our answers using Kirchhoff's current law. We know that the total current should be the sum of the current through the resistor plus the current through the inductor. And so total current, 2.623 milliamps at an angle of negative 40.326 degrees should equal the vector sum of 2 milliamps at 0 degrees plus 1.698 milliamps at negative 90 degrees. And so again, I'm going to look at these graphically. We have 2 milliamps at positive, at 0 degrees on the positive x-axis, and we have 1.698 milliamps at negative 90 degrees pointing straight down. And so we are looking for the vector sum, and again this forms a right triangle. And so the vector sum, we'll just need to apply Pythagorean theorem. If you converted these to xy coordinates, you would see that this was going to be the x component of the resultant, and this would be the y component. Just pay close attention that when the angle is at negative 90, the y component is going to be negative. So this is actually negative 1.698 milliamps because it's pointing down. And so 2.623 milliamps at negative 40 degrees, 0.326. We'll apply Pythagorean theorem. It'll be the square root of 2 milliamps squared plus 1.698 milliamps squared. And the angle will be the inverse tangent, always y over x. So you can see that this is the y component, this is the x component. And again, the y component is negative, so it'll be negative 1.698, that'll be milliamps, divided by 2, that's also milliamps. The milliamps will cancel. And so the total current, 2.623 milliamps at negative 40.326 degrees, should be equal to, and so we'll take the square root of 2 milli squared plus 1.698 milli squared, and we get 2.624, that's milliamps, and the angle will be the inverse tangent of negative 1.698 divided by 2, and we get negative 40.331 degrees. And so you can see a little bit of rounding error, but for the most part we're pretty confident that we have the right answers. So we think we have the correct current for the resistor and the inductor, and the correct total current for this circuit. Now that we know we have the right currents for the circuit, we can analyze the power. We'll start over here with the total power of the circuit. So let's look at the vectors. We have 24 volts at 0 degrees, and we have 2.623 milliamps, and that is at negative 40.326 degrees. And so we'll start with the volt amps. The total volt amps of the circuit is going to be just the magnitudes, multiply the voltage times the current, and we'll have 24 volts times 2.623 milliamps. So the total volt amps of the circuit will be, we have 24 volts times 2.623 milli, and we have 62.952 milli. The units will be volt amps. And now we will find the power, the total power of the circuit, which is going to be the volt amps times the cosine of the absolute value of the angle between the voltage and the current. And so what we're looking for here is the component of the current that is in phase with the voltage, and we find that by multiplying by the cosine. So the total power will be the volt amps, which we already have, is 62.952 millivolt amps, and we're going to multiply by the cosine of the absolute value of the angle, so 40.326 degrees, and so we have 62.952 milli times the cosine of 40.326, and we get power of 47.993. That'll be milliwatts. Last thing is the total bars, which would be the volt amps times the sine of the angle, again the absolute value of the angle. And so here what we're looking for is the y component of the current, which is perpendicular to the voltage. So the volt amps we already know is 62.952 millivolt amps, and we will multiply by the sine of a positive 40.326 degrees. And so our volt amps reactive, or VARs, total for the circuit will be 62.952 milli times the sine of 40.326 degrees. And so we get 40.738, that's milli, volt amps reactive, or VARs. And so I'll write these answers over here. The volt amps of the circuit is 62.952 millivolt amps. The power is 47.993 milliwatts, and the VARs is 40.738 millivars. Now let's look at the power for the resistor. We'll find the volt amps first. The volt amps of the resistor will be the voltage of the resistor times the current through the resistor, only the magnitudes. Voltage is 24 volts, and the current is 2 milliamps. And so the volt amps of the resistor will be 48, but 24 times 2 milli is 48 milli. 48 millivolt amps. Now, to find the power, the true power of the resistor, we will take the volt amps and we'll multiply by the cosine of the angle between the voltage and the current. And so here they're in phase. We have 24 volts at 0 degrees, and we have 2 milliamps at 0 degrees, and the angle between them is 0. And so we will take the volt amps, 48 millivolt amps, and we will multiply by the cosine of 0 degrees. And so the total power of the circuit will be 48 milli times the cosine of 0, which is 1, and so we get 48 milliwatts. And then we will find the volt amps reactive. Oh, and I wrote power total here. I meant to write power of the resistor. And here we're finding the volt amps reactive of the resistor. And so we'll take the volt amps, multiply by the sine of the angle. And so we have 48 millivolt amps times the sine of 0 degrees. And so the volt amps reactive of the resistor is 48 millivolt amps times the sine of 0. The sine of 0 I know is 0, but I'll type it in anyway. We have 48 milli, going to multiply by the sine of 0, and we get 0. 0 bars. Okay, 0 bars. And so I'll try to fit these answers in here. We have 48 millivolt amps. We have 48 milliwatts. And we have 0 bars. Finally, now we can look at the power for the inductor, and we'll start with the volt amps again. Volt amps of the inductor will be just the voltage times the current of the inductor. Voltage is 24 volts. Current is 1.698 milliamps. And so the volt amps of the inductor will be 24 volts times 1.698 milli, and we get 40.752, and that's milli volt amps. Now we can find the power of the inductor, which will be the volt amps times the cosine of the angle between the voltage and the current. And so we can see that the voltage is 24 volts at 0 degrees, and the current is 1.698 milliamps at negative 90 degrees, and so the angle between them is 90 degrees. And so absolute value of that angle. And so we'll take the volt amps, which is 40.752 millivolt amps, and we will multiply by the cosine of 90 degrees. So we have 40.752 milli times the cosine of 90, and we get 0. The power of the inductor is 0 watts. Finally, we'll find the volt amps reactive for the inductor, which will be the volt amps times the sine of the angle. So we'll have 40.752 millivolt amps times the sine of 90 degrees. And so the volt amps reactive of the inductor will be 40.752 milli times the sine of 90 degrees. Sine of 90 degrees is 1, and so we get 40.752 millivolt amps reactive. Okay, and so again, I'll try to fit these in here. Let's see, I've got 40.752 millivolt amps. I have 0 watts, and I have 40.752 millivolt amps reactive. And we know we have the right answers because the resistor has no volt amps reactive, has true power only of 48 watts. That's where the 47.993 milliwatts total comes into play, right? All of the power being dissipated comes from the resistor. And all of the volt amps reactive, 40.752 millivolt amps reactive, that is the same, minus a little bit of rounding error. about the same as we got for the total of the circuit. So all of the volt-amps reactive comes from the inductor. Now we have a series parallel combination circuit. We have 18 volts at 0 degrees running at 10 kilohertz. And we have an inductor, 65 millihenries, that is in series with a parallel combination of R1 and L2, where R1 is 5 kilo ohms at 0 degrees and L2 is 100 millihenries. The first thing we need to do is find X sub L for each inductor. So X sub L sub 1 will be 2 pi FL1, and so X sub L sub 1 will be 2 pi times 10 kilohertz times 65 millihenries. And so X sub L sub 1 will be 2 times pi times 10 kilo times 65 milli, and we get X sub L sub 1 is equal to 4.084 kilo. That'll be ohms, and inductive reactance is always at positive 90 degrees. And so now we can find X sub L sub 2. Again, will be 2 pi FL2. So X sub L sub 2 will be 2 pi times the frequency of 10 kilohertz times L2, which is 100 millihenries. And so X sub L sub 2 will be 2 times pi times 10 kilo times 100 milli, and we get 6.283 kilo ohms, and again that is always at positive 90 degrees. So X sub L sub 1 is 4.084 kilo ohms at an angle of 90 degrees, and X sub L sub 2 is 6.283 kilo ohms, again at positive 90 degrees. Now that we know the inductive reactances, we can start working on finding the total impedance of the circuit. And just like a DC circuit, we're going to want to start as far from the source as we can. And so we're going to start by combining R1 and L2. They're in parallel. And so R1 is in parallel with L2. And I will use the product over sum. So R1 times X sub L2, right, this is L2. Divided by the sum of R1 plus X sub L2. And so the product will be 5 kilo ohms at 0 degrees times 6.283 kilo ohms at 90 degrees divided by the sum 5 kilo ohms at 0 degrees plus 6.283 kilo ohms at 90 degrees. Now the product is the easy part. We will multiply the magnitudes and add the angles. So we have 5 kilo ohms times 6.283 kilo ohms, and we get 31.412. It's going to be mega ohms squared, and then we add the angles. 0 plus 90 is 90 degrees. Now the sum is a little bit harder, of course. Again, we have 5 kilo ohms at 0 degrees. We have 6.283 kilo ohms at 90 degrees, and we're looking for the vector sum. And so we're looking for the hypotenuse of this right triangle. We'll use Pythagorean theorem. We'll have 5 kilo ohms squared plus 6.283 kilo ohms squared. And the angle will be the inverse tangent of y over x. Y is a positive because it's pointing up. 6.283, that's kilo ohms, divided by 5. That's also kilo ohms. The kilo ohms will cancel. So R1 in parallel with L2 will be, the numerator is 31.412 mega ohms squared at 90 degrees, divided by, and we'll find the magnitude first. It's the square root of open parentheses 5 kilo, close parentheses squared, plus open parentheses 6.283 kilo, close parentheses squared. The magnitude is 8.03. 8.03. That'll be kiloohms. The angle is the inverse tangent of 6.283 divided by 5. We get 51.487. 51.487 degrees. Last step is now we can divide. R1 in parallel with L2 will be equal to, so we divide the magnitudes and subtract the angles. We have 31.412 mega divided by 8.03 kilo, and we get 3.912 kilo. Ohm squared divided by ohms is ohms, and the angle will be 90 minus 51.487. So we have 38.513 degrees. So that is the combination of R1 in parallel with L2. That is all in series with L1, and so we're ready to find the total impedance. The total impedance now for the circuit will be X sub L1 plus the parallel combination of R1 in parallel with L2. And so the total impedance will be X sub L sub 1, which is 4.084 kiloohms at an angle of 90 degrees, plus our combination in parallel, which is 3.912 kiloohms at an angle of 38.513 degrees. And so these vectors are not 90 degrees apart. We can't just simply apply Pythagorean theorem if the vectors are not 90 degrees apart. So we'll have to convert these both x, y coordinates and then add them and then convert them back to polar. And so the first vector, the x coordinate, we use the cosine. So it would be the magnitude, 4.084 kiloohms times the cosine of 90 degrees plus 4.084 kiloohms times the sine of 90 degrees, and that gives us the y component, or the j component, and we'll be adding to this vector, and so the x component is 3.912 kiloohms and times the cosine of 38.513 degrees plus 3.912 kiloohms times the sine of 38.513 degrees, J. And so the total impedance will be 4.084 kilo times the cosine of 90 degrees. Oops. Try that again. 4.084 kilo times the cosine of 90 degrees, which is 0, right? The x component for the inductor is 0, plus the y component, 4.084 kilo times the sine of 90 degrees, which is 4.084 kiloohms, J, and then we're adding to this vector. We have 3.912 kilo times the cosine of 38.513 degrees, and we get 3.061 kiloohms plus the y component now, 3.912 kilo times the sine of 38.513 degrees, and the y component will be 2.436 kiloohms, J. Now we can add the vectors. 0 plus 3.061 is just 3.061 kiloohms, plus 4.084 plus 2.436, So 4.084 kilo plus 2.436 kilo will be 6.52 kilo ohms J. Now we need this to be in polar coordinates. Eventually we'll go to find the total current. When we divide the voltage by the current, by the impedance, we're going to want this to be in polar form. So the impedance will be Pythagorean theorem, square root of 3.061 kilo ohms squared plus 6.52 kilo ohms squared at an angle of the inverse tangent of the y component, 6.52, divided by the x component, 3.061. The kilo ohms cancel. And our total impedance will be the square root, open parentheses, 3.061 kilo, close parentheses, squared, plus, open parentheses, 6.52 kilo, close parentheses, squared. The magnitude will be 7.203. 7.203 kilo ohms at an angle of the inverse tangent of 6.52 divided by 3.061, and the angle will be 64.851. 64.851 degrees. This will be the total impedance of the circuit, and so I'll write that up here. We have 7.203 kilo ohms at an angle of 64.851 degrees. Now that we know the total impedance for the circuit, we can find the total current. The total current will be the source voltage divided by the impedance. Source voltage is 18 volts at 0 degrees. Total impedance is 7.203 kilo ohms at an angle of 64.851 degrees. So the total current will be, we will divide the magnitudes. We have 18 volts divided by 7.203 kilo. And so we get 2.499 milliamps at an angle, and so we subtract the angles. 0 minus 64.851 is a negative 64.851 degrees. And so the total current for the circuit is 2.499 milliamps at an angle of negative 64.851 degrees. Now the total current for the circuit is the same current that flows through L1. So we know the current here now, it's 2.499 milliamps at an angle of negative 64.851 degrees. Now that we know the current in L1, we can find the voltage drop there. The voltage drop on L1 will be equal to X sub L sub 1, right, the inductive reactance of that inductor, times the current flowing through the inductor. And so we will have the impedance, or the reactance, of 4.084 kilo ohms at 90 degrees, times the current in the inductor, 2.499 milliamps, at an angle of negative 64.851 degrees. And so we're multiplying. We will multiply the magnitudes and add the angles. And so you have 4.084 kilo times 2.499 milli, and we get 10.206 volts at an angle. And so we'll add the angles. It's a 90 plus a negative 64.851 degrees, and we get 25.149 degrees. So the voltage drop in the inductor is 10.206 volts at an angle of 25.149 degrees. Kirchhoff's voltage law says that the source voltage must be equal to the voltage drop on the inductor, L1, plus the voltage drop on the resistor, R1. And so the sum of the voltage drops around any given loop must add up to the source voltage. And the voltage drop on R1 is going to be the same as the voltage drop on L2 because they're in parallel. So once we find VR1, we will also know VL2. And so we'll subtract VL1 from both sides. The voltage drop on resistor 1 will be the source voltage minus the voltage drop on L1. And again, this will also be equal to the voltage drop on L2 because they're in parallel. So the voltage drop on R1 will be equal to 18 volts at 0 degrees. It's the source voltage minus the voltage drop on inductor 1, which is 10.206 volts at an angle of 25.149 degrees. So to be able to subtract these, I will need them to be in rectangular coordinates. The source voltage is easy because it's at 0 degrees, right? We have 18 volts at 0 degrees. All of that is the x, none of it is the y. If you use cosine and sine of 0 degrees, you'll see that. And so the rectangular form of the source voltage is 18 volts plus 0 volts J. And then we're subtracting. Now here we will need to use the cosine and sine. I'll just type that into my calculator. We have 10.206 volts. And I'm going to multiply by the cosine of 25.149 degrees. And we get 9.239 volts. And then we will use 10.206 volts times the sine of 25.149 degrees. And we get 4.337, so plus 4.337 volts. That is the J component or the Y component. And now we can add our vectors together. VR1 will be 18 minus 9.239, so 18 minus 9.239, which gives us 8.761 volts. And then we have 0 minus 4.337, and so that's going to be negative 4.337 volts J. And so we'll want to convert this back into a polar form. And so to do that, we apply Pythagorean theorem. We'll take the square root of 8.761 volts squared plus 4.337 volts squared. And the angle will be the inverse tangent of the y component, which is negative 4.337 divided by the x component, which is 8.761. These are both volts. That will cancel. And so it's always a good idea to look at the components graphically. We have an x component that is positive. So we have 8.761 volts here. And we have a y component that is negative 4.337 volts, and we're looking for the vector sum, and so we want to make sure that we get an angle that is negative. And so VR1 will equal the square root of open parentheses 8.761 close parentheses squared plus open parentheses 4.337 close parentheses squared, and the magnitude will be 9.776 volts, and the angle will be the inverse tangent of negative 4.337 divided by 8.761. And so the angle is negative 26.337 degrees. And that looks about like what we're looking for, and so we're pretty confident that we have the right answer here. So the voltage drop on R1 is 9.776 volts at an angle of negative 26.337 degrees. It's the same voltage drop we'll have on L2. They will be equal. And so we'll have 9.776 volts at an angle of negative 26.337 degrees. Now that we know the voltage drops on R1 and L2, we can find the currents there. And so the current through R1 will be the voltage drop across R1 divided by the resistance R1. And so we have 9.776 volts at an angle of negative 26.337 degrees. And we'll be dividing by the resistance, 5 kilo ohms, at an angle of 0 degrees. And so we just divide the magnitudes and subtract the angles. So we have 9.776 volts divided by 5 kilo ohms, and we get 1.955. 1.955, and that'll be milliamps. And in the angles we subtract negative 26.337 minus 0 is still just negative 26.337 degrees. And so that will be the current through R1. We have 1.955 milliamps at an angle of negative 26.337 degrees. Same thing for L2. The current through inductor 2 will be the voltage drop across inductor 2 divided by the inductive reactance of inductor 2. And so we have the same voltage, 9.776 volts, at an angle of negative 26.337 degrees. And we will divide by 6.283 kilo ohms at an angle of 90 degrees. So we'll divide the magnitudes and subtract the angles. We have 9.776 volts divided by 6.283 kilo ohms, and we get 1.556 milli. 1.556 milliamps. And the angle will be a negative 26.337 minus 90, and we get negative 116.337 degrees. So now we know the current through L2. We have 1.556 milliamps at an angle of negative 116.337 degrees. Now that we know the currents everywhere in the circuit, we're going to want to check our answers using Kirchhoff's current law. And so we have current in L1, and when that current reaches a node, it will split. Some of the current goes through R1, some of it goes through L2. And so the current through L1 should be equal to the current through R1 plus the current through L2. And so we'll check our answers this way. We have 2.499 milliamps at an angle of negative 64.851 degrees. That's the current through L1. This should be equal to the current through R1, which is 1.955 milliamps at an angle of negative 26.337 degrees, plus the current through L2, which is 1.556 milliamps at an angle of negative 116.337 degrees. So I need to add these two together to check our answer. They are not friendly angles. We'll need to convert these to rectangular coordinates to be able to add them. So x coordinate, we use the cosine of the angle. Y coordinate, we use the sine. And so we will find the xy coordinates. We have 1.955. That's milli. We're going to multiply by the cosine of negative 26.337 degrees. The x coordinate is 1.752 milliamps. The y coordinate will be 1.955 times the sine of the angle. So this times the sine of negative 26.337 degrees. And we get a negative. I forgot to put my milli in there. This answer is actually supposed to be micro. So the y coordinate will be negative 867.336 microamps, and that is a J component. And then we'll be adding to this xy coordinates again. We have 1.556, that is milli. We're going to multiply by the cosine of negative 116.337 degrees. And we get an x coordinate of negative 690.319 microamps. Now we'll find the y coordinate, 1.556 milli times the sine of negative 116.337 degrees, and we get a negative 1.394 milliamps, and that's a J component. So now we can add these two vectors together. We have 1.752, that is milli, and we'll be adding to that a negative 690.319, and that is micro. So when we add the x components together, we get 1.062 milliamps. And now we'll add these together, the y components. We have a negative 8.67. Oops, I'm sorry, 867.336. That's micro. And I'm adding a negative 1.394 milli. And we get negative 2.261 milliamps J. And so to see if our answers are right, we need to convert this back to a polar form to see if it matches this. And so the polar form will be the Pythagorean theorem. We'll take the square root of 1.062 milliamps squared plus 2.261 milliamps squared. And the angle will be the inverse tangent of the y component, negative 2.261, divided by the x component, 1.062. These are both milliamps, that will cancel. And so we have the square root, open parentheses, 1.062, that's milli, close parentheses, squared, plus, open parentheses, 2.261, that's also milli, and that is squared. So we get a magnitude of 2.498 milliamps, and the angle will be the inverse tangent of negative 2.261 divided by 1.062, and we get negative 64.840 degrees. So again, we're just checking our answers here, and you can see that the current that we had in inductor 1 is in fact equal to the sum of the currents in R1 and L2. So using Kirchhoff's current law, we can see that we have the right answers here, minus a little bit of rounding error. Now that we know we have the correct answers for currents in the circuit, we can look at the power for the circuit. We'll start with the total power. Let's find the volt amps total first, which is source voltage times total current without regard to any angles. Source voltage is 18 volts. Total current is 2.499 milliamps. And so we get 18 volts times 2.499 milli. And we get 44.982 milli. That'll be volt amps. Now we can find the true power of the circuit by taking the volt amps total and multiplying by the cosine of the angle between the voltage and the current. And so again, if we look at these vectors, we have a voltage vector, it's 18 volts at 0 degrees. We have a current vector, that's 2.499 milliamps. The angle is negative 64.851. We'll use the absolute value of the angle between the two vectors. And so we already know the volt amps. It's 44.982 millivolt amps. We're going to multiply by the cosine of 64.851 degrees. And so we get 44.982 milli. We're multiplying by the cosine of 64.851 degrees, and we get 19.116. That's milliwatts. Now we can find the volt amps reactive. Volt amps reactive total for the circuit, and so that's going to be the volt amps times the sine of the angle. Volt amps is 44.982 millivolt amps, and we're going to multiply by the sine of 64.851 degrees. And so now we have 44.982 milli, and we're going to multiply by the sine of 64.851 degrees, and we get 40.718. 40.718 milli. That is volt amp reactive. Volt amps reactive. And so this will be the total power dissipation for the circuit. I've written the numbers for the total power of the circuit here. Now let's look at inductor number 1. The volt amps for inductor 1 will be the voltage of inductor 1 times the current through inductor 1 without any regard for the angles. Voltage is 10.206 volts, and the current is 2.499 milliamps, and so we get 10.206 times 2.499 milli, and we get 25.505. 25.505. That's milli volt amps. Now we can find the power through inductor 1, which will be the volt amps of inductor 1 times the cosine of the absolute value of the angle between the voltage and the current. And so again, it's helpful to look at the vectors graphically. We have a voltage that is at a positive 25 degrees, (25.149), and we have a current that is at negative 64, (0.851), and you can see that these vectors will be 90 degrees out of phase. If you add these absolute values together, you will get 90 degrees. So our theta in this example is 90 degrees. And so our volt amps, we already know, is 25.505 millivolt amps. We'll be multiplying by the cosine of 90 degrees. The cosine of 90 degrees is 0, and so 0 times 25.505 millivolt amps is 0 watts. The inductor uses no power. The volt amps reactive for inductor 1 will be the volt amps for inductor 1 times the sine of the angle. So we'll have 25.505 millivolt amps. We'll multiply by the sine of 90 degrees. The sine of 90 degrees is 1, and so 1 times 25.505 is going to be 25.505. This would be millibars. I've written our answers for power for inductor 1 here. Now let's look at the power for R1. We'll start with volt amps again. The volt amps for R1 will be the voltage through across R1 times the current through R1 without any regards to angle. The voltage is 9.776 volts. We'll multiply by 1.955 milliamps, and we get 9.776 times 1.955 milli is 19.112 volt amps. Oh, millivolt amps. Okay. Now we can find the power in R1 by multiplying the volt amps of R1 times the cosine of the angle, the absolute value of the angle between the voltage and the current. You can see that the voltage and the current have the same angle, so there's no angle between them. The angle is 0. And so we will multiply the voltamps, which is 19.112 millivolt amps, times the cosine of 0. Again, there's no difference in the angles between them here. The cosine of 0 is 1, and so 1 times 19.112 is 19.112. That would be milliwatts. Now we can find the volt amps reactive of R1, which would be the volt amps for R1 times the sine of the angle between the voltage and the current, which would be 19.112 millivolt amps, times the sine of 0. The sine of 0 is 0, and so 0 times 19.112 is 0 bars. So the resistor is not a reactive component. It has no volt amps reactive. It has all power in watts, no volt amps reactive. I've written our answers for power for the resistor here. Now we'll look at L2, the final component in the circuit. We'll start with volt amps. Volt amps for L2 will be the voltage across L2 times the current through L2 without any angle. And so the voltage is 9.776 volts. The current is 1.556 milliamps. And so we get 9.776 volts times 1.556 milli, and we get 15.211. 15.211, that's milli volt amps. Now we can find the power for L2, which would be the volt amps for L2 times the cosine of the angle between the voltage and the current. And again, let's look at the vectors. We have a voltage that's at negative 26 degrees. 26.337. And we have a current that is at negative 116.337. And again, you can see that the voltage and the current are 90 degrees out of phase with one another. That's always going to be the case with the inductor. The theta for the inductor will always be 90. So the volt amps we know, 15.211 millivolt amps. We're going to multiply by the cosine of 90 degrees. The cosine of 90 degrees is 0. And so 0 times 15.211 is 0 watts. The inductor uses no power. And the volt amps reactive will be the volt amps for L2. Will be the volt amps for L2 times the sine of the angle. Volt amps we know is 15.211 millivolt amps. Multiplying by the sine of 90 degrees. The sine of 90 degrees is 1. And so 1 times 15.211 is 15.211 millivolt amps reactive, millibars. And so these will be the power values for inductor 2. I've written our answers for power for L2 here. And we want to check our answers to make sure that these are correct. When we did this in DC circuits, we said that regardless if it's parallel or series or some combination of them, that if we added up all the powers of the resistors in a series parallel combination or any circuit, that it should add up to the total power. And that's still true for an AC circuit. And so the only component that has true power, or watts, is the resistor. We had 19.112 milliwatts for the resistor, and we had 19.116 milliwatts for total power of the circuit. So you can see they're fairly close, a little bit of rounding error. Now the volt amps reactive, we had two components, L1 and L2, that have volt amps reactive. We had 25.505 millivolt amps reactive for L1, and if we add to that the 15.211 millivolt amps reactive for L2, we're going to get 40.716 millivars. And so you can see that the sum of the bars of the circuit is very close to what we had for the total bars of the circuit. Now, in order to check the volt amps will not add up to be the total volt amps. And that is because, remember that the volt amps is the hypotenuse of a right triangle. One of the legs is power, true power, measured in watts. The other leg is the volt amps reactive. volt amps reactive is the Y component. And so the volt amps is the vector sum of the power and the bars, the power being at 0 degrees, the bars being at 90. And so I don't need to check this because we already know that these watts and these VARs will add together to give us those volt amps. And so that concludes this circuit.